In this chapter, we are going to discuss about gravitation, starting with Newton's laws of motion. The gravitational force acting between two bodies separated by distance r is directly proportional to the product of their masses and inversely proportional to their square of the distance between them. F equal to g m1 m2 by r square. G is the universal gravitational constant, which is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. R1 is the position of first particle, R2 is the position of second particle, R12 is the force between them, and F12 is the g m1 m2 by R1 minus R2 whole square into R12 cap. F12 equal to g m1 m2 by R1 minus R2 whole cube into R1 minus R2, which is equal to F12 equal to minus of F21. Superposition principle in scalar form. Resultant force acting on a particle due to other particle is vector sum of forces exerted by individual particles in it. F1 equal to F12 plus F13 plus F1n. Superposition principle in vector form. F1 equal to F12 plus F13 plus F1n. Kepler's law of planetary motion. Law of orbit. Every planet revolves around the sun in an elliptical orbit and sun is at its one of the foci point. Law of area. The line joins any planet to the sun sweeps equal area in equal interval of time. dA by dt is equal to L by 2m. Areal velocity is constant. Law of periods. The square of time period of a revolution of a planet is proportional to cube of semi-major axis of an ellipse. T square is proportional to r cube. T square equal to 4 pi square r cube by gm. Gravitational acceleration. At the surface of Earth, gravitational force equal to weight. mg equal to g m into mass of Earth divided by rc square. That is, acceleration due to gravity at surface equal to g into mass of Earth divided by rc square. Gn equal to gs into 1 plus h divided by rc. If h is very less than rc, then gh is equal to gs into 1 minus 2h by rc. Variation of g with depth. Earth surface. G at depth d, which is equal to g surface into 1 minus d by rc. Variation of acceleration to gravity from equator to pole. G equal to g minus r omega square cos square theta. Gravitational potential and gravitation potential. Energy required to bring a mass from an infinite position to a point under gravitational field of Earth with constant velocity. Potential equal to g m1 m2 by r. Generally, infinite is reference point. Amount of work done in moving a unit test mass from infinity to position to point under gravitational field of Earth. V is equal to gm by r, which is equal to u by m. If r is less than r, then potential is equal to minus gm into 3r square minus r square divided by 2r cube. If the both radius are equal, then v is equal to minus gm by r. If r is greater than radius of Earth, then potential equal to minus gm by r. Strength of gravitational field applied per unit test mass is defined as gravitational field density, that is E equal to minus gm by r square into r cap. Relation between gravitational potential and intensity. E equal to dV by dr. Delta V is equal to integral E dot dr. Weightlessness. During free fall under gravity inside a spacecraft or satellite, body is weightless. Effective weight of a body becomes 0. Geostationary and polar satellite. Geostationary satellite height from Earth's surface equal to 36,000 km. Radius equal to 42,400 km. Time period equal to 24 hours. Polar satellite. Height from Earth's surface equal to 330 km. Time period equal to 84 minutes. Orbital velocity equal to 7.92 km per second. Escape speed and energy conservation. Minimum speed required by an object to escape gravitational field of Earth, which is equal to root 2 gm by r, which is equal to root 2 gr. Escape velocity equal to 11.2 km per second. Orbital velocity equal to root gm by r. Total energy of satellite equal to a constant, that is kinetic energy plus potential energy is a constant. Total energy equal to gmm by 2r, which is equal to gmm by r, which is equal to gmm by 2r.